Good morning, everybody. Hope you've had a good evening and night out in London, and plenty of pubs and things like that. As Keith said, I've been involved with low carbon shipping for quite a long time. I was involved with the UCL study and the climate ships in changing climates project. So I've had a lot of experience. Doesn't mean I know everything, and basically, some lots of things change, but some things don't change, and the difficulty of making things change is quite one of the challenges. Getting ideas change. The work I did for the Energy Technologies Institute was with Black & Veatch, and we were sponsored by this non-governmental organisation to basically try and promote the introduction of energy-saving technologies, as well as means to reduce CO2 emissions, and obviously that means alternative fuels as well. And one of the things we looked at, as you can see at the bottom there, is looking at ship operations. How can we make ships operate better, more efficiently? The alternative fuels, and what we've done most of to date, and I was at gave a paper at the RENA Wind Propulsion Conference last year. We're looking at turbo sails, flattener rotors, and things like that. So one of the means to address the improvement of ship transport efficiency is basically the amount of CO2 emitted per tonne cargo nautical mile. And as you can see in this plot, there's various sources of information published by the Committee for Climate Change and other IEA and other sources. But basically, and then we've got the target set, or the requirements set by the IMO for improving ship efficiency. But one of the reports that have come out basically shows that ships are arguably going to meet these targets quite comfortably. So there's something to be said for future tougher regulation in terms of making ships behave better, if you like, operate better. And some of that, we've already had slow steaming. That's been a large part of why the efficiency has improved. Clearly, you go a bit slower, as you'll see, and due to the cube law, you're saving all of a sudden an awful lot of fuel. So that's good news on one side, but that's one of the things we're looking at. And just a plug for RENA's conference coming up later this year, the EEDI conference, which will be exploring future targets for the EEDI and ways in which we can improve the EEDI as a measure of improving ship design efficiency. So the challenge, as I see it, is clearly we've got the current IMO 2020 sulfur requirements to address. We had yesterday addressing the upsurge and uptake of LNG. But as you know, as was widely said, there's still relatively few ships that are using LNG bunkers. And going forwards, there's still a big question about what's going to happen, how are we going to address the need to reduce the CO2 intensity at the 2030 target, and of course the far off 30-year away target for 2050. So one of what I'll be talking about today really is some of the issues about where we are, what could we do, what other people are saying we're going to do, and why that isn't necessarily as easy as it sounds, and some of the ideas that I've got about why we might have alternative fuel sources which might be available sooner than some of these green methanol, green ammonia that you'll hear more of later on. So I'm going to talk about the current situation, the measures to reduce demand. Clearly there's a two-sided thing. There's reducing demand. We're doing it already with slow steaming. What can we do more? The current much discussed decarbonisation methods, and then what I call alternative fuels. Clearly a lot of this is speculative in terms of future ball gazing, but a lot of the information I'm giving you is based on where we are now in terms of my alternative fuels, but a lot of the numbers and how things might change, as you might expect, are speculative. So even though there's numbers, they're all based on the best information I could get, and some of the information, just because it's reported in a government document and such like, doesn't mean it's super accurate. So one of the observations is that even though people talk about ships growing at a phenomenal rate, the number of ships, the total gross tonnage, the actual growth of ships is, insofar as they can be measured accurately, is a steady but not over the top growth of about 1.2 arguably between 0.5% and 1.5% per year. So what I'm getting at is the kind of issues about loads of, doubling of ships by 2050. At the moment, there's no indication that that's the case. That doesn't mean it won't happen in the future, of course. So that's one of the other tricky things about future ball gazing, which is why addressing 2030 challenge is a bit more pragmatic, if you like. And the third greenhouse gas study undertaken for the IMO by UCL and its partners was published around 2012, 2013. And a lot of the data for that I've taken. I think there's a fourth greenhouse gas study currently underway. And I'm not sure when that reports. So clearly the data I'm using is as ever, out of date, and then at that time was as accurate as was possible. But what I've sort of looked at is some of the bigger vessels there, and the size ranges that were given. And as you can see, the principal contributors to total CO2 emissions is led by these, the bulkers, the containers, tankers to a lesser extent. And obviously, containers, massive now segment of world trade, arguably vulnerable to downturns in world trade, as we've seen with China, US trade issues, and obviously there'll be other issues now with the current health scare in China. So that's addressing the container market's very difficult. I've done a lot of work on wind-based propulsion technologies. You can't stick those very easily on container ships, so hence the need for other methods. And also we've in the paper you'll see I've used a nominal value of 223 million tonnes oil equivalent per year. The headline value that you see in lots of documents is about 300 million tonnes, which equates to approximately 900 to 1,000 million tonnes of CO2 per year. But I'm looking at that top set of ships when I look at the outcomes. And as I said, in the earlier slide, the transport efficiency is quite tricky when you look at it over, when you think about how can they do this accurately, quote unquote accurately. It's only an indicator that the ships, the activities of individual ships aren't always reported. There's no need for governments to know all about individual ships. The loads they're taking, they're not always fully loaded, of course, so that affects the data in terms of fuel consumed. And that's why the current IMO and EU means for measuring fuel or getting reporting of fuel is obviously going to help as a basis to inform future measures for monitoring and improving the efficiency of ships. And obviously you've seen that one before. What it does show, even in this period, ships were getting more efficient from mid-80s through as engines were getting more efficient and with the introduction of obviously common rail and other devices, more efficient turbochargers and such like. So we have had a trend, but clearly this trend, so this is why you might say, well, this particular target here wasn't a very austere target if you look at that kind of data. Apologise now, I'm going through these quite quick because I've got quite a lot of slides, and obviously it's all in the paper anyway. And one of the things I looked to try and reduce demand, the demand for fuel, tankers coming to Europe with fuel. One of the things I've done a lot of is looking at reducing the energy consumption of oil tankers. The irony being that those oil tankers are bringing loads of carbon to Europe to burn to make more CO2. So I thought, oh, okay, well, the UK's got quite a forward-looking target for reducing, for having 50% of the vehicles in 2030 sold as electric vehicles. And the plot there shows the kind of current trends. And as you can see, we're about here. And, even though there's the micro trend here does indicate this, it's still quite an ambitious target. But one of the issues was, even if all of these cars were obviously using electricity taken off the grid, ideally from renewable power, the amount of fuel reduced per year was about 3 million tonnes, and that equates to about 90,000 tonnes of fuel. So clearly not a big impact. So it's not a big impact for emissions in this country. The other area, reduced fuel, is ferries. Most of the ferries being used are in Europe, and obviously there's a large number of, I'm talking about ferries with vehicles on them, significant size ferries, not just foot passenger ferries. And one of the things I've fed into this is the fact that 50% of ferries would be battery driven. The general trend that's been reported is that if the energy used by the ferry on its voyage is less than 2 megawatt hours, then you can get the battery size and energy density is such that you can fit it, retrofit it. Clearly that arguably will get better as energy density increases and things like that, but that's something I've been looking at. And clearly Norwegian government, as was mentioned yesterday, they're very much looking to improve the emissions in their fields. One of the observations yesterday, I just want to clarify it, was that they want their ferries to be carbon neutral. And clearly this is going to be quite challenging when you've got some of the vessels that I saw there, had the benefit of seeing there last summer. I took this photo myself, and you can see how popular this is in terms of this hydrogen, electric-based vessel, but and the charging equipment, I think, is there. And what it does, it trickle charges from the grid, so that it can then do a very quick charge to the vessel when the vessel's alongside. So basically, all of this is like, but when you see the size of that vessel, clearly there's nothing to it. It's just a passenger vessel. So we've got a long way to go away from what you might call these kind of concept designs through to something which is of a significant size. And worldwide, there's scope for changing ferries, improving them. But the fact is, the biggest benefits are going to be the emissions from the stack, the NOx, the SOx, and particulate matter. So obviously, all of this work is part of an ongoing bit of study, and obviously this bit of reportage is mostly talking about what I think is happening at the moment, the potential for what could happen, and the bits we're going to do next is going forwards is the kind of timeline of how these things might happen and the costs that might be associated with it. Now, also to reduce demand on significantly large ships, we've got energy-saving devices, Flettner rotors and such like, wing sails and kites. We've got improved propulsion equipment. We could have contra-rotating propellers was an idea the Japanese were proposing a number of years ago. It's already well established on torpedoes and things like that. But it is tricky, and obviously one of the solutions is to have a podded propulsor forward-facing here, which matches up with that. Usually one's got 5 blades, the other one's got 4, and you get an improved propulsion coefficient with that. And I think there's a Japanese ferry that's got that on. But that hasn't proven to be so popular. Probably upfront cost, electrical equipment, more space just here. 3, and as I've mentioned, energy efficiency. Obviously, at the moment, engines are looking at issues with low sulfur HFO. That's got issues, challenges with the lubricating oil and such like, and also the addition of other fuels in the current fuel set. So that's one of the main challenges, as well as obviously operating with ethane and LNG and going forwards with that. So there's only so much they can do to improve the efficiency of the engine. So what else can they do? We look at waste heat recovery. Organic Rankine cycles are fitted to some ships from Japan as a basis, as a standard. I think they're mostly GE Calnetics versions. So you might get from 1,000 kilowatts of thermal heat, you might get 100 kilowatts electric out, and obviously that's a useful benefit. And then things like fuel cells and obviously air lubrication, which seems to be becoming more standard for slower vessels. What we do is when we analyse the electric, which we're trying to promote in a way that's independent, the uptake of wind-based devices, you'll know from the International Wind Association, that with Gavin, who, for those of you know all about it, he's very much promoting this, and we're supporting him on the basis it's the right thing to do, and there's a lot of choice. So we do studies for individual ships, look at their history from ship data, identify what happened to the ship on its voyage, and then identify what would happen if that ship were to have fitted a different equipment, so we can show the benefits of that equipment. And for those who don't know, there's Flettner rotors, which obviously is rotational. You get the benefit of thrust due to the Magnus effect, just like bend it like Beckham. If you spin a ball, hits the air, it will get a side force. These are wing sails off the Ashington, MV Ashington, about 30 years ago, if not more. And they were, until recently, sold by Ocean Foil. They've now gone into receivership, but there's other similar products available. And here we've got the turbo sail that we at BMT have been modelling using CFD. And there's a Dutch company that's also promoting that, Eco Wind. Thank you very much. Mr. De Vries is here, yes. And so that was proposed by the French diver, and what's his name? I've forgotten his name. But anyway, so we've modelled the turbo cell, which basically takes benefit of a suction area on one side, so that you get a lower suction side and on this side you get a higher pressure on this side due to the boundary layer being wrapped around further, and overall that gives a bigger benefit than if you didn't have the suction. So we've been looking at that. And one of the other issues about wing sails and all these equipments is fitting it on the ship. So we've got different places to fit the equipment, but it's got to meet the requirements for basically visibility from the bridge for coal rigs and SOLAS. So there's a summary there. I'm not going to go through it because I'm aware of time, but basically there's only so much we can do, 14%, by using energy-saving devices. So the current carbonisation methods that we've got, basically, a lot of this is the amount produced in the world, and if I convert it, basically there isn't enough, in ammonia, 150 million tonnes made in the world, methanol, 75 million tonnes. Putting aside just all the energy density, that's being used by industry already. So if you wanted to use ammonia and methanol combined, you'd have to sort of double the production, and that would and of course that new production, we'd want it to be green, wouldn't we? So that's why I'm saying it's a massive ask. So we talked about LNG, the methanol, very much sponsored by the Swedish government, but just to see the feasibility. But fundamentally, the feasibility, in my opinion, was proven already. So it's a useful exercise in terms of the supply chain and management and clearly safety, but actually it's not the answer. And also biofuels, there isn't enough biofuels. There's an issue with land use, issue with food, issue with quality of it, and also the fourth generation basically hasn't yet arrived, the algae-based fuels. Synthetic fuels, this again goes back to the green and blue ammonia and such like, more of which we've got two speakers about who I'll be much more articulate about. But fundamentally, this is all good stuff, but it's nowhere near arriving soon. So what did I look at? This is the main bit. Sorry about getting there slowly. So I'm looking at these main areas for supplying fuel in terms of what can we do, what's happening at the moment, how can we move some of this to our own pathways to ships. Forest growth. There's some good companies called Licella, CCAB, others are available, who are using waste wood, using hydrothermal treatment, 8-9 bar, 200, 300 degrees C. They break it down, basically hydrothermal liquefaction, to create a good black liquor which can then be treated either, and obviously the better quality could go to aviation and such like. And that's proven technology, but fundamentally the price has got to be right for that to happen for us. A lot of this forest growth in the United Kingdom basically is used to burn in so-called energy recycling facilities and arguably emitting emissions and not being used to the best ability. Just in the UK, we've got 2.5 gigawatts of capacity for reusing this kind of waste that could be migrated as obviously power comes from elsewhere. That the feedstock for those plants could be used arguably for our usage. And one of the key things is obviously analysing all the data, the declared data about wood that's being used, and it's a nightmare in terms of getting to the facts and how it's reported. But basically, there's about 1.874 million cubes of wood and such like, and a lot of this what I've done for each of these sectors is identify what I think could be created in the next 10 years, so by the year 2030 in a conservative approach. And so obviously I'm saying here about 34, which is one of the bigger sources. If you think about Finland, Canada and Sweden as principal sources, and obviously they are looking at this, hence the companies that I mentioned, they are looking at how this can be used to generate fuel. Processed wood, waste fuel, it's a much smaller feed, much smaller pathway, but clearly there's a lot of wood which is used from knocking down buildings, from the wood that's been used once and then is recycled. So there's 5 megatons from that. And one of the main areas is wood fuel. In Canada, there's a big push in some areas and even over in other parts of Asia to reduce the amount of wood burnt as fuel, because that gives local pollution, smog, smoke, just like the old days in old London town. And that's, so really we should be electrifying places, making sure that the amount of wood fuel that is used is reduced, both for local health, but also, as you can see there with the numbers, I'm not going to read out all the numbers, but there is a lot of scope for wood fuel to be used for a different pathway. But of course, wood fuel, that leads into wood pellets. Wood pellets have been growing. This country imports wood pellets from Canada. It's brought across the ocean, which in my mind is not the right thing to do. It's all driven by government incentives, so that the Drax power station can burn wooden pellets that have come from Canada. Wouldn't those pellets be better turned into liquid fuel in Canada and used for heavy, ice road truckers and all that kind of stuff in Canada, rather than wood being taken here to use in our power stations? It doesn't strike me as the right thing to do. So there's changing that pathway has scope. Waste from plastic, we all know that there's an issue with world plastic. It's again in the UK, we're quite familiar with it, with some of the reportage by David Attenborough and others. It's a problem that is most people have woken up to too late. But basically, there's a massive scope for treating plastic, again, in the same kind of way, turning it into isobutanol, which is very valuable for other processes in the chemical industry. But if the price is right, if there's enough of it, clearly the price will go down, and then that fuel the butanol and such like can be used as a drop-in for our world. So, I've done kind of generic ideas about how much could be used for fuel. It's work in progress, but it gives an idea of the amounts that can be taken. So all in all, it comes down to about 56 million tons of oil equivalent per year in the year 2030. And if you think about the 200, 250, that's about a quarter to a fifth of the total being used. So in a personal perspective, there's a lot of waste and wood that can be recycled, not just burnt and used as power gen in this country. If you think about it, I've looked at something in the Portsmouth area. Hampshire City County Council have got likely to have 100,000 more homes. Well, in Portsmouth, basically they have an energy recycling facility which takes in waste, burns it, and then makes electricity from that, which is great. But of course, it's just an incinerator, really, and that's emitting NOx and hydrogen chloride in the Portsmouth area. So within government standards, but that's, Portsmouth's one of the most densely populated cities in the UK. And so that fuel, that waste could be turned into liquid fuel and arguably be used by the Royal Navy or Southampton, could be refined in Fawley across the way in Southampton. So those kind of changing the pathways, moving the pathways to get waste and wood, which obviously is renewable. You might argue that using waste isn't kind of renewable, but the UK government in its policy for renewable energy includes biomass waste and other waste as a valid kind of part of the recycling economy. So that's why I'm adopting that. But basically that's my short and brief perspective on how pathways could change to get new fuel.